So, in this lecture, we'll learn about the virtual memory. And throughout the computer architecture path that you are walking with us, we have to resort to this mechanism where we first tell you a simple story, and then later on, we can elaborate on that story and tell you another story that's closer to what actually happens in a computer system. This is one of those moments, and you have had several of these moments already in 229. For example, in the beginning of the term, we said that there was only memory and registers, and later you learned that there were also caches. And now is the moment for us to tell you that the address that you use to access memory when you do a load or restore, or when you send the program counter to the memory to retrieve an instruction, is not actually the address that is used to fetch the data from memory. There is a level of interaction between those two. The address that the processor generates and the address that the memory uses to access the data are different. And there are very good reasons for those two addresses to be different. So it's one more of those moments of truth in your learning of computer architecture where you have to learn that there is another level of complexity that we need in order to build the computing systems that we use today. So first of all, let's look at the motivations for the use of virtual memory. And one important motivation is the protection of data. And to understand this motivation, let's consider that I have a user of Tinder. In this case, we have Emily here. And Emily is texting with someone on Tinder. And let's say that Emily is texting with Hunter. Let's stop for a moment and consider what is happening for this texting to take place into the phones of these two individuals. There must be a server somewhere that is processing this texting conversation. And in this server, there will be some code that will be the chat code for Emily, and there will be some other code that's the chat code for Hunter. And those two programs are two independent programs that are running in the same machine, and they are both accessing memory. If we don't take care, it would be possible for the chat code of Emily to access the data for Hunter or vice versa. Or what could be even more disastrous in this case, it may be that the parents of Hunter or the parents of Emily would have access to their chat. We don't want that. So we use the level of interaction with virtual memory in order to protect the data of one program against access by another program running in the same machine. And we also need to protect the data that is used by the operating system to manage the machine from access by the users for security reasons. So the first motivation for virtual memory is data protection and security. There is a second motivation for virtual memory, that is, we would like to provide an illusion of that we have a memory that's much larger than the one that we actually have. And this motivation started in the early days of computing. So I have to make a confession here and reveal something about my personal history with computing. The very first computer that I used was this computer. It's the IBM 1130. And this IBM 11, the way I programmed this computer when I first wrote my first piece of code was by typing in a machine like this one in the picture, that's a punch card perforator, and it would produce these punch cards that would contain the code, and then you would you see that piece of paper coming out of the machine that's processing these programs that are written in these decks of cards, and then you'd come back the next day to get the printout of your program, and if you had a bug or a mistake in your program, you had the opportunity to then retype your program and submit and wait for the next day for the test. So as you can see, this was quite difficult to do programming by monkey typing, monkey do kind of debugging, because it was 24 hours between executions of the program. The reason that I am not that old, the reason that I had this circumstances in my first year in university is because I did my undergrad in Brazil, and Brazil had some policies that prevented the acquisition of modern computers into the country, and we had technology that was quite old at the time. But let's take a look at this machine to understand the motivation that existed when these were the type of machines that were available. So this machine was actually introduced in 1965. And this machine has a 15-bit address space, so there are 15 address lines, but it had a maximum of 64 kilobytes of memory in the machine. And later, more recent versions of this machine could have up to 4 terminals, so you could actually type in the terminals instead of using the punch card data input process. But a Fortran compiler would run on this machine with 8 kilobytes of data. So the problem that we had prior to the creation of virtual memory is that the code would have to do the staging of the code itself in order to run. So when I wrote a piece of code, I had to first plan for which portions of the program should be loaded into the memory and executed, and then before I move to the next portion, I would have to again stage the program and the data into the memory before executing. So all the accesses to external disks were done by the program itself in the beginning. And of course, soon that got very old, because you're trying to solve a given computational task, and in the middle of the solution of your computational task, you have all this additional code that's to manipulate the movement of data between the memory and the external disks. Later on, more recently, when GPUs were first became popular for general computation, we had a similar situation where all the scratch memories in GPUs were also managed by the programmer. And today we have a hybrid solution for that level of computing. But basically, the idea that you have to do this staging was a great motivation for the creation of virtual memory. And if we jump to, this was a slide that I prepared a couple of years ago. So if you jump to the MacBook that exists in December 2018, that had an Intel Core i7 with 48 bits of address line, with 16 gigabytes of DRAM, and with a solid state drive with 512 gigabytes. So if you look into that, and we consider the address space that we have, that is the number of possible memory addresses that I can access based on the number of bit lines that I have, and I compare that with the number of bytes that I can store in memory and the number of bytes that I can store in disk, and I put this in a graph so that I have a visual comparison of those three, what I'm going to see is this. This long bar here is the address space. This is the number of bytes that you can access if you have 48-bit address lines. This is the amount of storage that you have in the disks. 512 gigabytes will be this big in comparison with the address space for the memory. And this here would be the amount of memory that you actually have in the processor as main memory. So as you can see, your address space is much larger than the amount of memory that you actually have in the computer. So what we're going to do, we're going to take advantage of this very large address space, and we'll try to create an illusion to the programmer and to any program running this machine that it can actually access this entire address space, or a very large part of it. We know that there are certain addresses that are reserved for the system and such, but we're going to give an illusion to a program that's running this machine that it actually can access a very large portion of the address space. The way we're going to do that is by making the use of the very same principles that we used for cache, that the principles of spatial locality and temporal locality. What we're going to do is have this 3-layer system, and we already know that this cache here could be several layers of cache in modern architectures, but let's just, for the sake of this discussion, consider that in this memory system I have a cache, a main memory, and then a disk where I can store more data. And the idea here is the same principle in the memory hierarchy. I can store more data in the main memory than in the cache, but the time to access this data is longer. And then I can store much more data in the disks than in the main memory, but the time to access this data is also much larger. Of course, the cost of storing the data decreases as I go down in the memory hierarchy. So it's the very same principles that we use for cache. So now let's consider with a picture example. We have divided the data that's in the cache into blocks before. What we're going to do, we're going to divide the data that's in main memory into pages. And a very common case is that a page is 4 kilobytes. So there will be 4 kilobytes in a page, and then I can take one of those and move into the cache, and this would be a cache block. So the cache, the unit of data moving between the main memory and the cache is a cache block. Then the movement of data between the disk and the memory, in the disk I divide the data into pages, and when I need to bring data between the from the disk to the memory, I'm gonna bring a page. So, but you can see the analogy between the relationship between cache and main memory, and between main memory and the disk. So the idea is that the main memory is used as a cache for the content of the disk. And this caching system is what we call virtual memory. The virtual memory, the cache that we studied before, is completely managed by the hardware. You do not have an interference between the operating system and the program when there is a cache miss. The processor simply waits until the hardware is able to fetch the data from the main memory. However, in the case of the movement of data between the disk and the main memory, the delays involved in this data exchange are much higher, much bigger. So what we have here instead is that the virtual memory will be managed jointly by the hardware and the operating system. So that's the idea of virtual memory. And to better understand how we do this this interaction, let's consider that I have a program A. In program, we now know that the addresses that the program uses are not real addresses, because we're going to do a translation to the real addresses where the data or the instructions are actually in the main memory. So we're going to, from now on, we're going to start talking about the virtual address space of a program. So this would be the virtual address space of a program A, and then I have the virtual private virtual address space of a program B. And then I have the physical address space, that is the actual main memory. This is where the data is actually stored. I will divide my virtual address space into pages, and as I said, a common case is that we're going to use pages of 4 kilobytes. And we're going to have a different division also of the private virtual address space of the program B. And we'll divide the memory address space into frames. So we talk about pages in the virtual space and frames into the physical space. And now what we need to do is to have a mapping. And this mapping will map the private virtual address space from the program into the physical frames in the memory. So I could have this mapping here that is mapping all the pages from the virtual address space of program A into the physical address space, into the frames in the physical address space. And I will have another mapping that's for my program B that also going to do this mapping. And in some cases, I may have a page from multiple programs mapping to the same frame, and that is done for the two programs to be able to talk with each other through accesses to memory. But whenever you do that, you need to first ask permission to the operating system to share that page. So that is done in the beginning of the execution of the programs. And then there will be issues of synchronization to the access of those pages. We have studied synchronization with the load reserve and store conditional instructions that we had studied before. Now you know that this will happen in those shared pages that have been pre-registered with the operating system. So this is the mapping that I have. The hardware and the operating system will implement this address translation and will jointly maintain this mapping. The address table will also implement a protection mechanism. We're going to see in some more detail the control registers used in RISC-V for this protection mechanism. So one of the questions that we need to answer right away is the same thing that we did when we studied cache, when we had to decide what to do when a block was not in the cache when requested. What happens if a page is requested by the processor, but it's not in memory? This is a virtual memory miss, the equivalent to the cache miss, but in virtual memory is not called a miss, it's called a page fault. So if the processor is requesting an access to memory and the corresponding page is not in main memory, what we have is a page fault. So the address translation will be something like this. I'm going to have the virtual address for, in this case, one program that's executing, and some of these addresses will be mapped to physical addresses, and I can access. Those are the accesses where I do have the data in memory. And then some of the accesses will not be in memory, and I'm going to have some descriptor that tells me where they are in disk. And in order to access them, I will have to retrieve them from the disk. There is a virtual memory address, and what I'm going to do, if my page is 4 kilobytes, I can separate this address into two portions. One is the page offset, that is how far down the page this specific word that I'm requesting is in that page. And the other is the virtual page number. That is the bits that remain after I have used all the bits that I needed to index the page to find the word in the page. So naturally, that index into the page does not need to change between the virtual address and the physical address. It can be the same. So how far down a word is in the page can be the same distance in the virtual address space and in the physical address space. But then in so the translation will not gonna change the page offset. The page offset will be exactly the same in the virtual and the physical space. However, the virtual page number will be translated to map to the correct frame in the memory. So the virtual page number gets translated into a physical page number. And the number of bits that you use it for the virtual page number or for the physical page number is determined by the address space. So in this case, I have a virtual address of 32 bits, and by the number of bits that are actually implemented by the memory system. So in this case, the memory system, the physical address, has 2 fewer bits than the virtual address, because in this example, the memory space does not implement all the addresses that are the same number of addresses in the virtual address space. So the length of those 2 addresses does not need to be the same. So what we have here is that we have the cache, we have the main memory, and we have the disk. And the exchange of data between the cache and the main memory is very fast. So it only takes hundreds of cycles at most for us to bring the data from the main memory into the cache. So this is completely handled by the hardware, and the processor, when there is a cache miss, will simply wait for the result and will not going to change what it's doing. However, the amount of data that has to be transferred between the disk and the main memory, because that exchange is done into pages, and the overhead of managing the translation and managing placement of pages and such by the operating system, makes the fetching of the data between the disk and the main memory to be much slower. So it can take millions of cycles for us to do the replacement of a page that suffer a page fault. So what we're going to do instead, we're going to have an exception to the operating system, and we'll have a context switch in that case. A context switch means that the program that's currently running will stop running, and another program will be scheduled to run at that time. So the operating system will put the current program to sleep, while another program will come in to run. So you may ask, well, if the program that's needing the page goes to sleep, who does the transfer between the disk and the memory? And if the transfer is accessing the memory anyway, isn't it interfering with the execution of the program by the processor and the fetching from the cache? What happens is that there is a mechanism called direct memory addressing, DMA, that allows the operating system to simply give a command to a separate chip. It's a small processor or controller that will manage the transfer between the disk and the main memory. And when that transfer is completed, an exception will be generated, and the processor will be told that the transfer is complete and that page is now available, and then the operating system will be able to reschedule the program that had suffered the page fault for execution in the processor. So one of the important things for performance is that we must minimize page fault rate, which means that we don't want to have more page faults than we have to. One way to do that is to make the mapping between the memory and the disk full associative. Remember, full associative means that any page that's blocked from the disk can go into any frame in the main memory. So there is no restriction such as 2 or 4 or 6 or 16 way set associativity. Any page can go anywhere in the main memory. And the other thing that will help us is to have very smart replacement algorithms, and that is a domain of operating systems. When you take the operating systems course, you're going to understand much better the replacement policies that you need in order to make an effective use of virtual memory. So here is a picture illustrating the translation using a page table. So the idea of the page table is that the page table contains the translation that we need to do to find out what is the frame in the main memory that corresponds to an access that's being done by the processor. So what we have is there is a page table register that contains the address of the beginning of the page table, and we're going to look at this in more detail for RISC-V in the second part of this lecture. But there is a register here that indicates the beginning of the page table. And then I take my virtual address. As I said before, the page offset does not need translation. It's the same in the physical and the virtual address, so it passes directly. I take the remainder bits from the virtual address, and I use these remainder bits to index the page table and find in the page table the corresponding physical page number for that access, and that corresponding physical page number then is provided by as the physical address. And then I also need to check whether that translation is actually valid. And there will be, as we're going to see in detail in the second part of this lecture, several additional bits here that are protection bits that will tell me whether I can actually access that page at this time with this program. So the page table registers in the CPU will point to the start address of the page table in the memory. The page table is indexed by the virtual page number, and there are several techniques to do this indexing. It's not simply taking all those 20 bits and accessing a memory that is 2 to the 20 entries. Because the active translations, actually, the number of pages that actually need translation in a given execution of the program is much smaller than 2 to the 20. So we can use hashing, or you can use some kind of radix table. So there are different techniques to make this indexing. But conceptually, what happens is that I take the virtual page number and I index the page table to find the translation. So if the page table is in memory, it will contain the physical address, the reference bit, the dirt bit, the protection bit, etc., all going to be needed for protection. If the page is not in memory, this will contain the location in swap space or in disk. So to summarize, this is another view of the translation. I have the virtual page number. I index a page table, and as I said, this index is not a direct indexing like we are used to indexing the cache, for example. There is sophisticated ways to do this indexing to minimize the amount of space that I need for the page table. But anyway, the concept is that I do an indexing, and when I get there, I find out whether that translation is valid, so whether I have a valid translation, and then I find out whether I will find the data in the physical memory or whether I need to go to disk to retrieve the data. So I'm going to stop here the first half of this lecture. In the second half, we're going to look at how virtual memory is implemented in RISC-V.